Alright, everybody. I'm Meyer. I'm sorry for everyone behind me, but I'm not actually going to look at you for most of this. But I'm from Georgia Tech with the Marine Robotics group there, and today I'm going to be talking about simulation for autonomous robotics. Really kind of want to talk about why, when, and how you're going to simulate things to actually get the most advantage, what has worked and hasn't worked for us. It's just a little bit about us. I'm from, again, the Georgia Tech Marine Robotics group. We participated in the AUVSI Marine Robotics competitions. We kind of restarted back up in 2016. And since then, we've participated in RoboSub, RobotX. We've been successful to varying degrees in those different competitions. A little better in the surface vehicles, not quite as great in sub, but we've learned a lot of things. We're part of the Aerospace Systems Design Lab at Georgia Tech. And so that's a graduate systems lab, and so advise a lot of the undergrads. Really, we specialize in systems engineering and design of vehicles. And we've got 15 years of experience working with O&R and the NEAT programs. And our team is pretty academically diverse. We've got 3 graduate students that basically work on as advisors to the different teams, 15 plus undergrads split between the 3 competitions. And some of those students are also getting research credit as well as they're going through this. So quickly, just going to talk about why we need simulation, because I would hope most of us kind of understand that simulation is a very useful tool in the development of autonomous robotics. And so I'm sure many of you understand that the design of these smaller marine robotics is a very difficult problem. It's very tightly coupled in that small design decisions are going to affect each other, and you can't necessarily make one decision before making another. A common example of this is going to be sensor selection. You can't necessarily make any sort of controller design algorithms until you've done sensor selection. But the optimum sensor is going to depend on some of your other design decisions as well, and so you get kind of stuck in this chicken or the egg problem. Hardware experimentation can really help with this, but there are some serious issues with that. It's expensive. If you're doing sensor selection by buying sensors and then testing them, half the sensors you buy, at least, are going to just kind of be wasted money. You still need some sort of prior verification and validation before you can get out and test those, because the marine environment's really harsh. If you haven't done any sort of simulation, it's possible that if you put a sub out into the water for the first time without ever testing it, you might not get that hardware back. So one thing that's nice is simulation environments allow you to do some virtual experimentation and verification before putting it out for the first time. Hardware in the loop simulation is really nice. It allows you to kind of even further go on in that verification process. And hardware in the loop also allows you to do some debugging and iteration in a more lab-like environment before you get out to that harsh kind of unknown. So just looking at kind of the generic design process, it's going to be design, build, test. Simulation really just kind of adds a separate layer to that, of where you can simulate before you actually build and test that. You can think of it as either another layer or as an integrated testing environment. And so it does something. So for like sensor selection and placement, that's one of the things we've really found useful in simulation, is you can actually simulate the sensors beforehand, either by looking through manufacturer spec sheets, trying to come up with sensor models that match those. Even if they're not perfect, they can give you a good idea of the performance you can expect. You can then develop kind of sensitivities and say, okay, if we could design our perfect sensor, what would we want, and what's the closest we can actually get within our budget. It also allows you to play with that coupling between sensor placement and selection, so you can actually kind of study that as you're making decisions on your vehicle. The biggest part, especially for us, because we're, and I'm sure many people are, somewhat budget limited, it allows you to kind of put off your significant purchases of sensors until you actually have enough information to say, yes, this sensor is going to be worth the extra money or not. It also allows you to kind of reduce the off-site testing that you have and the testing that's done outside of your lab. And so for the pool testing, for the sub, that's not necessarily that big of a problem to go and either work with a pool or something like that, but we've had time limitations, as I'm sure everyone has had. So if we can limit the amount of time we need in the pool and make that as efficient as possible, it's going to be helpful for us. For larger competitions like RobotX, we also simulate a lot, because being from Atlanta, there's not really an ocean anywhere nearby, so putting out a large vehicle into the water is a little more difficult. And so
kind of the goal here is kind of unify the field testing and the lab testing so that you get a lot more efficiencies throughout. And so how do you use simulation is an important thing to think about before you actually go through and just say, I'm going to make the best simulation environment in the world. And so what we've used simulation for are kind of these four main things. We look at a down selection of alternative algorithms, largely in perception. And so those two bullet points there are kind of important to remember. Positive performance in the real world is going to imply that positive performance in the simulation. So basically what that means is if it works in the real world, it should work in your simulation. Because most of the time, your simulation is going to be much easier than the real world. You're not going to have random noise and a lot of things that you would see in the real world or random failures that you would see. However, you don't get to say the same thing going forward. If it works in simulation, that doesn't mean it's going to work in the real world. But if it doesn't work in simulation, it's probably not going to work in the real world as well. There are some cases, like that's not a hard and fast rule. But in general, if you can't get it to work in simulation, it's probably not worth the time and effort to get it to work in the real world. So you can use this to basically compare and eliminate choices in algorithms. Another thing that this is kind of nice for is once you've validated algorithms that are working in the real world and brought those back to the simulation, you can now compare those and say, okay, my performance of this algorithm is performing better in simulation than this other algorithm. I'm going to devote more effort to actually tuning this. You can also do a lot of coarse tuning of control algorithms. What I mean by that is you're not going to get exactly the gains you want on your PIDs or something like that. But you can get in the right ballpark so that once you actually make it to the pool or to the lake or wherever you're doing your testing, you have a much closer idea of, okay, this is exactly the gains I actually want. The last thing that's really big is simulation is much easier to debug than it is in hardware. You can visualize all of the failures. You can see what your robot is actually thinking as it's going through and doing something. And so visualization is really one of the key elements of a good simulation environment. The other thing you can use is if you have a hardware-in-the-loop simulation capability, you can actually do hardware debugging. Why is my motor not turning? Is my pressure sensor actually responding correctly? Things like this. You can test in the lab before you go out again, and it's much less frustrating in a nice air-conditioned environment than out at the lake when it's humid, it's hot out, anything like that. So a couple things to kind of consider as you're building up these simulations. You got to look at your physical modeling. So are you going to make a parametric versus a non-parametric model? So what I really mean by that is it going to be kind of starting from first principles physics and building up from there, or are you going to do something like a neural network model of your dynamic behavior and just kind of tune to data that you've collected? Those are very different things. If you use a parametric model, chances are you can kind of generalize that to other vehicles as well. And sure, you have to retune your parameters, but it's kind of more extensible. The non-parametric models aren't going to be as generalizable, but they're generally going to give you slightly better performance. And so it's kind of a trade-off there of what do you really want. It's also kind of the inclusion of physical phenomena. So basically, what sort of fidelity am I trying to give to these physical models? In perception model, it's kind of the same deal, is you have this trade-off between you can use probabilistic perception, which is basically saying, I don't know exactly what my algorithm is going to be, but I can know it's going to be 80% accurate. I'm going to have like a 95% or like a 5% false negative rate, things like that. So you can model it perceptually or probabilistically, or you can actually integrate the perception into kind of sensor models and actually see what's going on. So the extent of your perception modeling can determine or will be determined by the perception or the fidelity of your sensor models. And so this kind of goes back to you want to match the fidelity of your models to the goals of your simulation. So if your goal is to just make a simple proof of concept of some decision making, low fidelity vehicle dynamic models are probably fine. You don't need to know exactly what's going to happen if you turn your motors at 10% more versus 10% less. But you're going to need moderate to kind of higher fidelity perception and behavioral models because that's really what you're trying to do. You don't need the highest fidelity because you're just doing a proof of concept, but you want to make sure that things that you think are going to work do. Another example would be if you're kind of tuning some control algorithms, it's probably the opposite. You really don't care about your perception and behavioral necessarily. That's going to be at a higher level than what you're considering. But your vehicle dynamics should be very high fidelity if you're actually going to be trying to tune some of these parameters. And so I'm going to talk a little bit about the simulation environment we've developed. We developed this in-house. It was in C# on Windows. It uses kind of a publish-subscribe message passing architecture. It has many simulated sensors, including LiDAR, cameras, hydrophones, GPS, and IMU. The LiDAR and GPS, probably not useful to you guys at RoboSub, but we do some of the surface vehicles as well, so that's where those come from. It's largely kind of non-parametric models informed by real-world testing and validation. It's capable of simulating vehicles in different environments, and it utilizes kind of this modular data pipeline, so you get hardware in the loop capabilities and playback capabilities of sensor logs. So talking about this modular data pipeline, basically we have three different sources of data that we can take. We can either take simulated sensors, we can take past log files, or we can take actual hardware. And essentially, we treat these the exact same. So it's just using a simple data format that basically says, okay, this is the information I'm coming in, this is what I'm going to pass on to the actual simulation framework. And then it just does some checks to say, okay, which data source am I actually pulling from right now, and how is that going to be passed on to the rest of the framework? Kind of the keys with this, though, is this allows the hardware in the loop simulation. The rest of the simulation doesn't care whether you have a simulated sensor or a real sensor giving it information. It's going to act on that the same. The other nice part about this is code that you've developed in simulation on simulated sensors should be able to be deployed to the real vehicles with real sensors. You can also then test your new algorithms against old data to see, okay, was my perception going to pick up that gate that I missed with an older version of this algorithm? It's a little more limited in doing controls and decision making on logs, but you can at least say, okay, would it have made the right decision even if I then can't project into the future? And so within the simulation, this is kind of the data flow. And I'm going to cover this a little quickly because everyone's probably going to have this slightly different depending on how they've set up their control architecture. But essentially, the data flows from our sensors to some filters. So this is going to be a state estimator, an identifier, a classifier, something like that. It then gets flowed to the missions. And so those missions are just going to be some task description. And that's going to tell us what are we actually taking in from these state estimators and classifiers. That gets passed on to an arbiter, which is kind of our high-level control algorithm. It's a path planner. That gets passed down to a lower-level controller that turns, okay, what's my path plan into actual motor commands, things like that. And those then get sent to the actuators themselves. One of the nice parts about this, though, is because we use that publish-subscribe message passing architecture, you can skip or go back to, or however you would like, steps in this data pipeline. So if you follow this, you will get a working kind of simulation or robot going. But you could try and implement kind of an optimal controller, so doing something that actually takes into account like your energy use or something like that. So then you could combine basically two of these steps, the arbiter and the controller, into one. So as we've implemented this on hardware, we've done 3 of the surface vehicles, so the Robot X vehicle, 2 of the RoboBoat vehicles, 2 underwater vehicles, so 2 RoboSub vehicles. We've participated in these competitions and also used those vehicles for other bits of research, doing path planning and things like that. The simulation has been really key because it's allowed us to iterate on these algorithms really quickly. And so you can kind of see what we've got on the right there. We've got a comparison on the top of simulated images versus the real images, and it does a decent enough job of that. And on the bottom is kind of showing what's going on in RoboBoat, of where you can actually see some of the visualization of what is the robot thinking. So I'm just going to very quickly demo some of this software, if I can get out of here. And so as it pulls up, this is basically the layout of it. You can see we have some simulated objects. This is actually all pulled from last year's competition. So we've got our vehicle here right now. I've got keyboard control of it, but we can actually see what's going on with the sensors. And so we've got a simulated camera looking at that. And now you can see some of the visualization. So we can see, yeah, it is actually picking up that camera. So if I give it control, it'll start moving actually towards that camera or that gate and try and pass through it. It's kind of nice to have that visualization again, so you can see, okay, which parts are breaking down, which parts aren't breaking down, and I can put the robot in different places. So I can see, okay, what if we come at it from an angle? Is it going to fail? And you can kind of check on what your failure modes are going to be. Back into this. I think. So just quickly, some of the advantages, because we have this unified environment, so the same software that we use to simulate is the same software that runs the vehicle. Algorithms that we develop in simulation go straight to the vehicle itself. And again, the visualizations, kind of one of the big keys, work for all three data sources. So whether it's in simulation or actually on the physical hardware, we get the same visualizations. We have nice hardware in the loop simulation capabilities. So we can do driver and hardware debugging issues in the lab, and it kind of provides another level of confidence that, hey, we know that our simulations are actually turning our motors in the correct way, things like that, so that as we move it into the pool, we have a little more confidence in what's going on. Then you have the ability to replay both real-world and simulated experiments to say, okay, I came up with a new algorithm. Did it work on this data that I was failing on before? And it allows you to visualize what was failing and what was succeeding. There are limitations. So our biggest limitation is probably that we're Windows only, and so we're only minimally compatible with a lot of kind of the de facto marine robotics standards. And so that's this year we've actually been working a little more with ROS and trying to develop some of those compatibilities, but it's pretty basic at this point. The sensors and actuators that we've implemented are pretty limited because it's really the ones that we were looking at. It's not going to be a generic LiDAR that you can just plug in and see, okay, does a LiDAR actually work on my vehicle? The other thing is there's lots of simulations out there. I don't really suggest going out and starting from scratch, kind of like we did. I think using Gazebo or AppSim, or there's a lot of different simulations you can go to, like a Unity framework, are probably going to work fairly well and probably going to give you better results than saying, hey, I'm going to start from scratch. And that's kind of the main limitations of what we've been dealing with. And so just to kind of conclude quickly, I wanted to talk about some of the things that I think are the most important for making a successful simulation. The first is that you actually have to understand what you're trying to do. Are you just doing an exploratory simulation of where you're trying new things, you're just doing proof of concepts? Or are you doing an exploitative design of where I have an algorithm that I know kind of works, now I want to actually tune it? That's going to really determine what fidelity you need on models later on. It's also understanding, am I looking at physical behavior of my robot, or am I looking at decision making of the robot itself? Those are going to determine what models I really care about the most. The second, and probably one of the most important, is that you need to visualize everything. Visualization is really what makes simulations useful. If you can visualize what the robot is thinking, why it's making certain decisions, what it's seeing, that's going to be the most useful when you're debugging and going through and seeing what worked, what didn't work. It's also important to remember that kind of earlier what I was alluding to is you need to go back and test still. You can't really do everything in simulation because you're going to have stuff that is taking advantages of small inaccuracies in the simulation. So going through and intermittently doing some hardware testing is going to allow you to calibrate your models and identify major errors of your models earlier on. The last part, and it's probably the most boring part, and the part I like the least as an engineer because I just like making things, is documentation. That is crazy important, especially if you're going to pass this on to something else. And I know it's one of our weaknesses because just because you wrote something and you understand how it works does not mean the person you hand it to is going to understand how it works. And so having that documentation, being able to point someone to the resource of saying, this is actually how this function or this model is working, that way you can go back when something fails, as it will, you can say, okay, what do I need to understand and where are my problems likely to be? So with that, I'm going to just open it up for any questions. Yeah.
Can you elaborate a little bit more on hardware in the loop? What is it good for? When should you do it, when you shouldn't, and some examples?
Yeah, so our biggest use of hardware in the loop is basically just doing some basic sanity checks. We do some hardware in the loop for testing control algorithms. So one of the things we do is do simulated motors with a actual IMU. So we can basically take our vehicle, hold it, and physically rotate it and see, okay, are we rotating as we should be in the simulation environment? Are our motors turning as we expect them to? I'm trying to think. Can you repeat your question again?
Just with the use of hardware in the loop, just I guess what I'm really looking for is just examples of how you've used it and its benefits.
Okay. So it's largely going to be in debugging. If something, as we were running in the pool goes wrong, we can then come back and say, okay, let's put ourselves in a similar situation in the simulation and see what bits of hardware are either working or not.
Can I just expand on that question?
Can do.
I think that not an answer, but another follow up is that you're saying you're using like a real IMU in your simulation. How do you match the values so that say you're trying to do like positional estimation through your aggregator, and we are like your state estimator.
Sure.
How do you match that IMU so that you know that like when it's in the simulation? Because when you move in the simulation, how do you feed that back in to the hardware?
That is a great question, and it's something that we don't actually do. So we're not like, there's no feedback loop when we're doing hardware in the loop. Does that make sense?
Right.
Yeah.
So you guys are like, but when you turn the thing, does it actually respond to the simulator?
Yeah, and so essentially what we're looking for are changes in the IMU, not necessarily the actual values themselves. So as we turn, we look for what's the change in our orientation.
So do you like instrument the motors to see if they're actuated properly?
Yep. Yeah, and so, no worries.
Yeah, but for the motors that you guys actuate, like, do you guys have something in the lab that, like, because you know you're not supposed to run them out of water.
Yeah.
So how does that work?
So we have a small setup. It's basically a trash can with a bunch of water in it. And so we can run the motors underwater, and we also have some force sensors as well. So then we can pass some of that force information back into the simulation and see how it's responding. Yes?
Do you have any tips for like getting started with simulation if you've never used it before?
So my tip would be to look at what's already existing. I know depending on what you're using, like if you're using ROS, Gazebo is a great source. It's a large built-up simulation that has a lot of packages already available. I would start by asking yourselves what you want to get out of it. If you just want to do some proof of concept stuff, even just basic like a MATLAB simulation of, okay, is my control law actually going to turn me left when I want to turn left, is probably like, it might not be what you think of when you think simulation, but it's enough to give you those ideas. All right, am I missing anyone?
When you showed your implementation of the visualization,
Yes.
the part that was more three-dimensional, what were you using a particular library? Did you use integrated C#?
It's OpenGL, and then that was largely built on our own. One of the previous students in this team had built kind of a CAD integrator, and so you could build up whatever you wanted in SolidWorks, and that would then generate the OpenGL pieces that could then be linked in. Does that make sense?
Yeah. Was it, do you know how long the CAD integrator took, or was it like a long project, or was it like something they finished quickly?
It was relatively short. I want to say it was a couple months, not like an entire year.
So was the simulation running on the robot's computer, or did you have it communicating with another system?
It was running on the robot's computer itself, and so the same software that was simulating was also our control software.
Okay. I imagine simulations can be quite intensive. Would you want to move that off to another computer and have it interact with the robot's computer?
It would depend. So if what you're trying to do is run a lot of things in parallel, then yeah, you'd want to run that somewhere else. Or if you're using some higher fidelity models in your simulation. So a lot of our stuff was relatively quick to run just because we had the hardware limitations. But if you wanted to integrate, like say, computational fluid dynamics to do your dynamic model instead of a fit model, then you would want to run that on something else, right? Because there's no way our little computers could run CFD at any sort of reasonable rate. Sure.
How do you know if your simulation is actually like good enough to reflect reality?
That is a great question, and it's a very difficult question to answer. Largely, it's done through actually doing some verification in the pool. So a lot of it's qualitative at this point. We're working on developing some kind of actual numbers to back it up. One thing we've done with physical dynamic models is you can take your logs and see if you can actually predict your logs given the same inputs. And that will give you the closest that we've been so far to like a hard number of accuracy of the model. Does that make sense?
Yeah.
Anybody?
So any reason in particular you chose to do it C#?
Yeah, it was largely because it was some familiarity of the original team. We were also focusing on developing on the Windows side because we're an aerospace department. A lot of the undergrad students that we work with have zero familiarity with Linux, and so lowering that barrier of entry was kind of one of our goals. Yep. Any other questions? All right. Thank you all.